talking about simple regression analysis. Last class I gave you some basic introduction, essential introduction to the concept of regression analysis and simple regression analysis. Okay? So we're going to continue it today. So at the end of last class, we've seen how to run. Well, this is an example, right? And in this example, we have independent variable of the size of the house in square feet, okay? And we have house price in $1,000 as the dependent variable. Okay? So the story is, what is the effect of the size of a house on its price that we're trying to estimate. Okay? So we have collected some data. It looks like we have about 11 observations here. Okay? So you have collected the size and price information on 11 houses. Okay? And first of all, you can create the scattergram like this, which will give us some rough idea, okay, on what the relationship might look like. Looks like we have some positive correlation here, right? Which is, of course, logical, right? The larger the house, the more expensive the price would be, right? And then you can run the actual regression, right? And let me show you how to do that here in Excel today. Okay? So first step is choose the data right here, clicking on the data here. And the second step is click on the data analysis, and then you choose regression. Okay, so here we have actual Excel file open. Okay? And click on data and data analysis, and we have a few choices here, and you choose regression. Regression in Korean language is 회귀 분석. So choose that one and click OK. Right? All right, now we have to enter our information for y variable and x variable. Okay? All right, here I have some actual data. What does it look like? Any idea what this is about? Yeah, this is my grade book, right? One of my, I guess, previous classes grade book. And of course, I deleted all the names and personal information. Okay? But there's homework 1 score, homework 2 score, exam 1 score, final exam score, absence, participation, and based on those numbers, I calculated average, okay? Final class average. Okay, so let's say, you want to know the relationship between the, let's say, first homework score and the average. Well, let's say final exam score, right? What is the relationship between final exam score and the final average? Okay? Then, which is independent variable and which is dependent variable? Which do you want to use as independent? Let's choose two variables. Now we are running simple regression, one independent and one dependent, right? So what about final exam and final average? Which should be the independent? Final exam score should be independent, right? Obviously, I mean, based on the final exam score, I calculated the average, right? So logically, final exam score should be the independent variable, right? What's causing the relationship, right? And the actual value of the dependent variable, which is final average, okay, should depend on the final exam score. Okay? So y-axis range should be here. Just start from the label. The first row is label of each column. Okay? Just highlight the whole column. Okay? And then x variable should be, of course, final exam score. Okay, I think the last row here, these are averages, average of all the variables, right? So don't include the average. Okay? All right, and since we included the label, you check the label here. Let the computer know that the first item, first observation is not actual observation. It's the label of the column or the variable. Okay? And then that's all you need, basically. And here you have some output option. Okay? Either you can have it on the new worksheet, or you can specify certain area on the current worksheet if you want to see the result, right? So if you just do it like this, then you're going to have the result on the new worksheet, right? But yeah, let's try new worksheet. And yeah, right now you don't need to check anything here. I'll tell you what to do later. Yeah? Just click OK. All right? And then I have all this result immediately. It doesn't even take thousands of a second, right? And I told you last class about 30 years ago, when they didn't have these personal computers, we had to use this handheld calculator, right? And obviously I have about 40 students in that class. Just entering all the number, right? That's after entering, it takes about, I don't know, at least 25, 30 minutes to actually calculate just two parameters, just the slope and intercept. No other statistics provided here, right? As we go on, you'll see the Excel has provided a lot of information here in this printout, right? But just to calculate two numbers, the slope, estimated slope and estimated intercept, it takes about 25 to 30 minutes, right? So we're living in an amazing world, right? Okay, so here, we'll talk about all these things later, right? But here, it says y-intercept, and here's the variable final, right? Final exam, okay? So what we're looking for immediately are these two numbers, right? So we have final exam as independent variable and final average as the dependent variable, okay? And we were looking for, so we have y and x, okay? And y as beta naught plus beta 1 x, okay? That's the model, okay? And once you estimate it, we have it y hat is b0 plus b1x. Of course, once you estimate it, the epsilon, the error term drops out, right? Okay. And apparently, we have 35.26 plus 0.49, 0.49x. Okay? Yeah, so that's how, okay, this output came around. Well, using the house price example, they came up with the 98.248 plus 0.109x. Okay? All right, so in this example, we have estimated equation this way, 90.248 plus 0.109 square feet. Yeah? First of all, we are not going to deal with the intercept. We are not interested in, or we are not worried about the intercept, right? And why is that? Why are we not concerned about the intercept? Yep. Right. Okay. So when we have actual data, right, and estimate an equation, right, the intercept means, well, this is B0, right? Intercept means, well, if x variable was 0, right, then y variable would have this value, right? But in many cases, 0 is out of the range of our data points. For example, in this case, the x variable is the size of a house in square feet, right? And can you think of a house with 0 square feet? Right? There's no such thing, right? So this number is meaningless, okay? But we need it. Why do we need it? What do we need it for? I said it's meaningless, but that doesn't mean you can throw it out. Right? We need it for what? What purpose? I explained it. Right? If you go back to the video recording of last class, I certainly explained it. Right? When do we use this intercept number? Yeah. I'm sorry, what? Out of variable?
It was to calculate the other variables.
Okay, I see. Well, if you really want to calculate it by hand, you have to estimate the slope first, okay? And then use the slope to calculate the intercept, right? But the intercept is needed to make a prediction, right? So once you estimate this relationship, ultimately we're going to use this equation for prediction purpose. Well, this is the different example, right? But here we have 98 plus 0.10977, right? So in case you have a house with, say, 2,000 square feet, right? Then you want to know what will be the price of this house, right? On average, right? In the market, if you have the house with the 2,000 square feet in size, right? What will be the market price, right? That's the idea, right? So when we have the equation 98.24 plus what? 0.11 x, right? So if you have, say, 2,000 square feet, what will be the price? Right? That's the idea, right? Because if you don't know the intercept, if you only know the slope, right? Then that line, well, we know the slope, 0.49, right? But we have not determined a single equation or single regression line because there are what? Infinite number of regression lines with the same slope, right? And in that case, you cannot make any prediction. Should we use this or what, right? For a certain value of x, right? So we need the intercept to determine the height of the regression line, right? And then once you have the slope and intercept, you have determined one single particular regression line, okay? And then you can make a prediction, okay? However, again, don't try to interpret the meaning of the intercept. It has no meaning. It's just the only function of intercept is determining the height of the regression line, okay? What about B1? the slope. That we bother a lot. We first try to interpret the meaning of the slope, and then we put it to the test to see whether this is a reliable estimate. Okay? Because that slope basically tells us the relationship. Well, here we have what? 0.10977 as the estimated slope, right? And what is the meaning of that slope? Well, you know, the slope of a line, that's change in y divided by change in x, right? Rise over the run, right? So what that means is for each time x increases by a certain unit, let's say 1 unit, right? Then y goes up by this much, right? So, well, this here, we have measured the x value, if you remember, right? Y value, square feet. The x is measured in square feet, but y is measured in $1,000, okay? So when we say 0.10977, right? For every 1 unit increase in square feet, right? The change in y is 0.10977 times $1,000. Okay? So that's $109.77, right? So every time house size increases by 1 square foot, right, the price increases by $109.77. Okay? All right? All right. Go back to this grade book example. We have this estimated equation. Okay? Can you interpret this value, 0.49? Remember, x was the final exam score, right? And y is the final average, right? And we got 0.49 for the slope estimate. Can someone try to interpret the meaning?
It's like 1 more point in your finals increases your average by 0.49.
Exactly, right? So every time you get 1 more point, 1 point higher in the final exam, right? Your final average increases by 0.49 point, right? About half a point. Okay? That's what that means. Okay? What about this intercept? Again, we're not trying to, we're not interested in the meaning of that intercept because I don't think anybody gets 0 in the final exam, right? Unless the person misses the final exam, right? But even then, if the person missed the final exam and got 0, right? Well, literally, this means if someone had the 0 in the final exam, his or her final average would be 35, right? But obviously, that's not very meaningful, right? Because usually, in normal situation, nobody gets 0 in the final exam, right? But if someone got 0 by missing the final exam, obviously that relationship is not going to be accurate. Okay. Okay. All right. So back to this house price example, we have interpreted the meaning of the slope, and then we can use the equation to come up with the predicted value, right? So if you're looking for a house with 2,000 square feet in size, okay, then you can say, well, expected price or predicted price in the market is about $317,085. $317,850. Yeah, sorry, $850. Okay. Does it make sense? Okay. All right, so here's one more reminder about this interpretation of the intercept, why we are not making, we're trying to interpret the meaning of the intercept, because we have a range, certain range of the data points. Yeah? So if you're talking about the house price, yeah, probably the usual size of any house would be somewhere between 500 and maybe, I don't know if it's a Bill Gates house, maybe 80,000 square feet. Okay? But typical house is about between 500 and 5,000 square feet. Right? So your estimation will be valid within that range, right? Outside the range, try not to extrapolate the information, right? Because we have no idea what's happening outside this range, right? The actual regression may go up this way or go down this way. We have no idea. We have no data, right? So we have to always be, remind yourself the prediction, interpretation are valid only within the range of the data. Okay? All right, let's go on. So we know how to estimate, and now we know how to interpret, okay? And we also know how to make a prediction, how to use the equation to make a prediction, right? The next step is testing, right? So before you actually use the equation and make an investment, so you spend money to purchase a house or something, right? You have to see whether this relationship is reliable, or how trustworthy your estimation is. Is this really accurate, right? So the next step is we're trying to come up with some measure of accuracy, okay, of this estimation. Okay? Here's some basic equation here. SST is SSR plus SSE. Okay? Sum of square for total, or total sum of square of variation, is equal to regression sum of square plus error sum of square. Okay? And total sum of square refers to this thing, right? yi minus y bar. What is yi? Yes, individual y value, right? Because we have many y values, right? What about y bar? Grand mean, I told you, right? It's the mean value of all the y values, right? So let me go back to slide, slide number 9 here. Yeah? You've seen this graph last time, yeah? So we have actual y value here, yi, okay? And let's say this is the grand mean value y bar, okay? So out of all the y values, we have this grand mean here, right? So the total deviation, total difference between actual y value and y bar is here, right? So here, you can call this total deviation, the distance or difference between yi and y bar, okay? And this yi minus yi hat is, actual value minus predicted value, right? Because you're going to use this equation, you're going to use this regression line to make a prediction. So you plug in xi to the equation, and then you're going to get estimated value right here, right? And last class I told you that's unexplained deviation, while this is explained deviation, right? Remember the story? If you have no idea about the regression analysis, right? If you have no idea about even the relationship linear relationship between x and y, right? And someone asks, okay, what do you expect for your tomato crop size this year? You're taking the notes on your cell phone? Hyojin? Okay. I've been watching you a long time. All right. So here, this, without knowing anything about the regression analysis, probably the best answer is y bar. Okay? Just average. Okay? But if you have some idea about the relationship between x and y, let's say the effect of fertilizer on the size of tomato crop, then you may use the regression analysis and say, well, according to my past history, okay, if I use 10 ounces of fertilizer this year, I'm going to get, I don't know, 150 pounds of tomato, right? Something like that, right? So this deviation, the difference between the predicted value and just the mean value, is explained by what? Explained by the amount of fertilizer you use. In other words, the size of x variable, right? Meaning you have used the regression analysis, right? So you can say either way. You can say it is explained by the independent variable or explained by the regression line, okay? And yet, you made this error because actual tomato crop size came out to be this high, right? While you predicted only this much, right? So this difference is the error. In other words, unexplained deviation, unexplained difference, okay? Well, we have the same relationship here. So this slide is simply another way of putting it, okay? Instead of deviation, yi minus y bar, y hat minus y bar, and so on, we have converted it into sum of squares, okay? Remember why we square all the deviations? Because before you add up, if you just simply add up all the deviations, then some deviations are negative, some deviations are positive, right? So negative deviation will cancel out the positive deviation. So if you just add them up, you're not going to have accurate measure of total error you are committing, right? So in order to avoid that problem, we square each deviation and add them up, right? So this is simply the sum of square for total, or sum of square of the total deviation. And this is the sum of square for what? Between explained and unexplained deviation. Which one is this? Predicted value minus grand mean. That's explained deviation, right? Explained by the regression line, right? So we call it SSR, sum of square for regression, or regression sum of squares, okay? And finally, we have the difference between actual value and your predicted value. Obviously, this is your error, unexplained deviation, right? So we call it sum of square for error, or error sum of square, right? Depending on which textbook you use, some textbooks call it TSS, RSS, or ESS. Well, most of the textbooks use SSR and SSE. But some textbooks use TSS instead of SST. Okay? But yeah, just in case you see it, you know that's the same thing. Okay? Okay, so this is a very obvious relationship, right? Out of the total variation, we're talking about out of all the variations, these y variable or y values, right? Some are explained by the regression line, some are not. Okay? The question is, how much of the total variation in the dependent variable is actually explained by the regression line, right? So, we have all this variation of y values, right? Let's say your regression line explains only 10% of the total variation in y value. In other words, in my previous example, the amount of fertilizer you use, right? It explains only 10% of the variation in the tomato crop size. Then obviously it's not a very good predictor, right? You're not going to get a very accurate prediction of the tomato crop size you're going to get if you make it based on the amount of fertilizer you use, right? Okay? So that's what we are trying to understand here. Okay? I explained everything here: total variation, explained variation, and unexplained variation. Okay? So once you calculate those numbers, okay, we can calculate coefficient of determination. We call it R squared. Okay? Concept of R squared is that it's the portion of the total variation in the dependent variable, y, okay, that is explained by the variation in the independent variable. Okay? R squared can be calculated by dividing SSR by SST. Going back to this, right? Dividing SSR by SST, and that's going to simply give you the portion, right? Right? How much of the SST is actually explained, right? And obviously, the larger the better, right? And all right, going back to the actual Excel output, the second table here is called the ANOVA table. In English version, you're going to see ANOVA. Okay? Analysis of variance. Analysis of variance. Okay? It's cool. And here we have regression, error, total. Regression, error, total. Okay? And degrees of freedom, this means degrees of freedom, and this is sum of squares and mean squares, F score, F test, or F statistic, and this is p-value for F statistic. Okay? Forget about F and P right now. We'll talk about that later. Okay? But what matters here is SS, sum of square and mean square. Okay? So sum of square for regression, this is regression again. Okay? So this number, 2695.665, that's SSR, regression sum of square. Okay? And 3282.31, that's SSE, right? Error sum of square, right? So when you add them up, you get total, right? The bottom number here, that's the SST. Okay? So if you want to know R square, what should you do? What's the size of R square in this case? How do you calculate it? 정우? How do you calculate the R square? Okay. Anybody else? You don't have to give me actual number, but how would you calculate R square? What? Okay. What's the SSR according to the printout? Right. 2,695.665 divided by 5,977.975, right? That's going to be the R square, right? Right? Okay. If you actually calculate that, then you're going to get right here, 0.4509, right? Again, sorry about using the Korean version of Excel, right? This in English version would say multiple r, and this is r square, and this should say adjusted r square, right? And this is the standard error and the number of observation. Okay? So apparently I had 40 students in that grade book, right? Total number of observation was 40. Okay? And in this regression, the r square came out to be 0.45. Okay? If you divide 2695 by 5977, you will actually get this number 0.4509, right? All right, can someone interpret that meaning? R square, 0.45. What does that mean? We got R square of 0.45. One's up. Positive relationship? Is that what R square tells us? You're talking about R, right? R correlation coefficient, right? Yeah, correlation coefficient is 0.67, right? So obviously it's a positive correlation. You can say relatively strong, right? Because it's greater than 0.5. But it's not that really strong because it's not like 0.9 or 0.8, right? It's 0.67. So you can say there is relatively strong positive correlation. But I'm asking for R square of 0.45. What does that tell us?
If an independent value changes by 1, a dependent one is affected by 1.
No, you just interpreted the slope. Slope is here. Slope 0.494, right? That's what you said, right? You said what? Independent variable increases by 1 point, y would go up by 0.49, right? I'm asking for this number. Okay, here. That's R square.
It says that we got some variance value, then that value, the percentage, the portion of the specific variance.
I think you know the concept, but I didn't use those words, right? Systematic or whatever. All right, here. Okay, going back to this slide. Right? Coefficient of determination is the portion of the total variation in the dependent variable that is explained by variation in the independent variable. Right? Make sure you understand and remember this concept. Right? R square gives us the percentage of the total variation in the dependent variable, which is explained by independent variable, right? So in our example here, we got 0.45, right? Can someone try again? Here, independent variable is final exam score. Dependent variable is final average, right?
Of the total variation of y, about 0.45% is explained by...
Not 0.45%. It's 45%. Yeah. 45% of what?
The total division of y.
Total variation in the dependent variable, in this case, which is final average, right? So 45% of the variation in the final exam, final average, is explained by final exam score, or variation in the final exam score. All right? You have to be able to say that, right? So in general term, the R square gives a percentage of or portion of the total variation in the dependent variable y, which is explained by the variation in independent variable x, right? Okay? I guarantee that that will be on the exam. Okay, so here we have, okay. We have the printout for house price example. Oh, we have English version here. Good. We have multiple R, R square, adjusted R square, standard error, and observations. Okay? And R square is 0.58. All right, can someone try? What does that tell us? Tajun, want to try?
Sorry, I wasn't paying attention. I was reading.
You were reading? Okay. Anybody else?
58.08% of the variation in house prices is explained by variation in square.
Perfect. Excellent. Excellent. Right. So 58% of the variation in the house price is explained by the variation in the size of the house. Okay? That one variable, size of the house, explains about 60% of the variation in the price, house price. Does it make sense? Okay? So obviously, higher the better. Higher the better, right? And in textbook example, you can have 0.8, 0.9 example, right? 80%, 90%, right? In reality, though, if you do actual research, R squares tend to be relatively low, especially if you're dealing with the simple regression, just one variable, right? I mean, think about it, right? If you're looking for your house, I mean, trying to buy a house, you may use real estate agent. Okay? This is what I learned from my real estate agent when I was trying to buy my first house in Cleveland, Ohio. Okay? And she told me there are 3 things you have to consider when you buy a house. Does anybody know those 3 things? First thing is location. Okay? Where the house is, right? Location of the house. Second thing is location. Third thing is location, right? That's what she told me, and that's a well-known fact in real estate market, right? So according to that, well, the size is not really important, right? But location is the most important determinant of the house price, right? Which is true. Okay? It's same in Korea. You have heard of Gangnam, you see, Gangnam district, right? But even in the United States, in one city, there is a certain area where, well, high-income people are concentrated, high-income families, right? And that makes the school better, I guess. I mean, they hire better teachers, whatever they do, provide a better environment and facility for students. Okay? So that school zone is very important, even in the United States. Okay? Anyway, okay, so that's the concept of R square, or coefficient of determination. Okay? You should be able to interpret that number. Okay? All right, so R square, actually, the concept is SSR divided by SST, right? As you see here, the regression sum of square divided by total sum of square, right? But why do we call it R square? Okay? R square. Because it is R square. Okay? What is R? Correlation coefficient, right? So when you have this X variable and Y variable, you can calculate R, correlation coefficient, right? And if you square it, that's going to be R square. Okay? That's kind of interesting happening right there, right? Because R, what does R measure? Correlation coefficient? R gives us what? Two things. By looking at the number R, we can see two things, right? First is just R, yeah. Right, whether it's positive or negative, which means we can see the direction of the relationship between the two variables, whether they are positively related or negatively related, right? And then also, by looking at the size, right, or absolute size, what does that tell us?
Whether it's a strong or weak.
That's right, strength of the relationship, whether there's a strong linear relationship or not very strong linear relationship, right? So in that sense, I guess it makes sense because if you really have strong, think about it. All right. If the data points are scattered right around the regression line, not much variation, right? Then the total variation will be, the variation of y values right there, right? But let's say this is y bar, right? So you pick any point here, let's say this point, right? So total deviation is this much, right? What about the explained deviation? Explained deviation is the difference between the predicted value and the grand mean, right? So here, this is the predicted value, right? Explained deviation is this much. Unexplained deviation will be what? Very small, right? So if you look at this ratio here, SSR divided by SST, right? SSR will be almost as large as SST, like 0.8, 0.9, right? Does it make sense? Because if I'm talking about R, suppose correlation coefficient came out to be 0.95, and make it 0.9 to make it simple, right? And that tells us there's a positive correlation, and it is a very strong correlation, which means there isn't much deviation, right? As opposed to if you have same regression line, but if the data points were scattered widely, right? Then if you look at this, suppose this is y bar, grand mean, right? Then this is the total deviation, right? Explained deviation is only this much, right? Unexplained deviation is that large, right? So if you calculate R square in this example, it's going to be relatively low, right? So if you calculate R in this case, well, it's a positive correlation, but you may get something like 0.2 or 0.3, right? Because obviously data points are scattered in the wide range, right? And you don't have really strong linear correlation, okay? All right, so you have to have understanding of that relationship. R can be negative, as I explained it previously, right? It can be between -1 and +1, right? But R square obviously cannot be negative, right? So it's between 0 and 1, right? R square is between 0 and 1. Okay, so if you have all the data points on the line exactly, of course, then what? You're not making any error, right? So your error sum of square, SSE, will be 0, which means what? If SSE is 0, then what's true? SSR is equal to SST, right? In other words, your regression sum of square will be equal to total sum of square, which means, right, everything, or 100% of the total variation is explained by your regression line, right? If you have this relatively wide scattered data points, right, then it will be between 0 and 1, right? Can it be 0? Well, yeah. If R squared is 0, if you have something like this, right, then it is possible that R is 0, right? Your correlation coefficient will be 0, and that means R squared can also be 0, right? In other words, nothing is explained. I mean, none of the total variation in Y is explained by your independent variable, right? It will be highly unlikely in realistic case. All right, so we have how to find R squared in actual printout. We talked about that already. Okay. All right, standard error of estimate is another measure of the fit. Again, I told you regression analysis is about line fitting. We're trying to find the equation of the best fitting line through the data points, right? So standard error, well, R squared was one of the measures of the fit, right? How useful the regression line would be, right? Obviously, if you have high R squared, right, something like, okay, if you have R 0.9, then R squared would be 0.81, right? Which means 81% of the total variation in your dependent variable is explained by your independent variable, right? Then you can say regression line is quite useful, right? Because when you make the prediction, you will be, well, quite accurate, right? Using that information, right? But here, standard error of estimate is another measure, right? We use SYX in this textbook, right? In most other textbooks, they call it S epsilon, standard error of estimate, right? S epsilon. Okay? Okay? And this measures the variation of observations around the regression line. Okay? So, we've talked about 3 variations so far, right? The total variation was the variation of Y values in the entire data, okay? And then we separated into unexplained and explained variation. Okay? This time we are introducing another variation, right? When think about the Y values around the regression line, right? Right? How widely the data points are scattered around the regression line, right? And obviously, based on what we've learned so far, right? The ideal case is what? Smaller variation, right? If the data points are scattered around the regression line tightly, right? Then obviously we're not going to make a lot of mistake or error when we make the prediction, right? Again, this is the regression line, and that's our prediction line, so to speak, because whatever x value you have, you're going to plug in that value to this regression equation, right? Which means your predicted value will be right there, right? And, well, in that case, you don't want actual data points to be far away, right? If the actual data point is far away, that means you have a lot of error, right? But if all the data points are around the regression line like this, then your error will be pretty small, right? So standard error estimate gives you that idea, right? How tightly the data points are scattered around the regression line, right? So the smaller the better, right? In ideal situation, you will have very small standard error estimate. That is simply SSE divided by n minus 2 square root, right? What's in? Okay. I guess I need to give you some explanation about this degrees of freedom thing, okay? If you were in my class last semester, I gave you some idea. Okay, where's that printout? Here, okay, here. You see degrees of freedom here? Okay, degrees of freedom for regression is 1, residual 8, total degrees of freedom is 9, okay? And in this example, we had the 10 observations, right? Observation is 10. So n is 10, right? So in this regression, it was n minus, total degrees of freedom was n minus 1, okay? And total degrees of freedom for regression is 1, degrees of freedom for residual. Residual is the same thing as error. Residual means remaining, right? So what's remaining after explaining the variation, right? What remains after the explanation, right? So, in other words, what's still unexplained, right? That's well, error, right? Degrees of freedom for error is 8, which is n minus 2, right? Why do we have these numbers? Let me try to give you quick ideas on the degrees of freedom. I mean, in statistics, we frequently hear the word the degrees of freedom, right? But let me just try to give you some insight. Okay? All right, so we have, let's say, I tell you, we have a sample, and the sample size is 5. Okay? Can you come up with these 5 numbers? Well, you're free to choose any 5 numbers if I say that, right? If this is the only condition I give you, right? That means you are free to choose any 5 numbers, right? You can choose negative zillion starting from, right, to positive zillion, right? And you can say 2.6978143, right? Whatever you want, right? So in this case, degrees of freedom is 5. You can choose any 5 numbers. You are totally free to choose 5 numbers, okay? But if I say, okay, n is 5 and sample mean is 3, okay? Then you can choose any 4 numbers. But once you choose 4 numbers, the last one is already determined, because it has to satisfy this condition, right? Okay? You can try with any simple number, like minus 10, 5, let's say minus 5, 5, 10, whatever, right? Then, silly, well, then what would be the x? Try to make it very simple, right? It's 15, right? Because when you add them up, whatever, this is 0, right? 0 plus x. So x divided by 3, x divided by 5 has to be 3, which means x has to be 15, right? You see that? Okay? So you can choose any 4 numbers, but once you do that, the last number is determined, which means you have lost 1 degree of freedom. Degrees of freedom there is 4 now, right? Why? Why did we lose 1 degree of freedom? Because we have estimated 1 parameter, right? Unknown parameter, mean, right? So every time you estimate 1 parameter, your sample loses 1 degree of freedom. That's a simple idea, insight, right? If I say, okay, well, we have 5 observations, but mean value is 3, and standard deviation is 1.2, right? Then you can choose any 3 numbers, but the rest, the other 2 numbers are determined, right? In order to satisfy these 2 conditions. Okay? So that's the idea of degrees of freedom. Okay? So in the statistics, every time you estimate 1 parameter, you lose 1 degree of freedom. Okay? So here, the general formula later in next chapter, when we talk about multiple regression, right? I'll give you the formula, right? The degrees of freedom for regression is number of independent variable. We usually use K, right? If you have 2 explanatory variable or independent variable, degrees of freedom will be 2, right? The total degrees of freedom is always n minus 1. Or, yeah, okay? So the residual, the degrees of freedom for, okay, degrees of freedom for regression is K. Total is n minus 1, right? And degrees of freedom for residual, which is error, what should it be? Because this one plus this one has to be n minus 1. Degrees of freedom for residual would be, in general, huh? N minus what? Minus K minus 1. Yes. That's the general formula for residual degrees of freedom, N minus K minus 1. Okay? All right? So we're talking about simple linear regression in this example. We have only 1 independent variable. So degrees of freedom is 1, 8, 9. If you have n is 10, right? We have 1 independent variable, right? So degrees of freedom for error is n minus 2. Okay? All right? So we have SSE divided by n minus 2. So you can say what's inside the square root sign is a variation. Oh, I'm sorry, variance. Okay, I didn't talk about that, right? Well, just quickly. In today's class, I use the word variation a lot, right? Variation in y variable, right? So on, right? When I say variation, I mean SS, sum of squares. Sum of square deviation, right? If you divide the variation by degrees of freedom, if you divide the sum of square by degrees of freedom, it becomes what? Any idea? Variance, right? Typical variance you've learned so far, right? Variance of x was a summation xi minus x squared divided by what? N? or n minus 1 if you use sample mean, right? So, keep that in mind. When I say variation, I mean sum of squares, right? And if you divide the sum of square by degrees of freedom, it becomes variance, okay? So what do we have inside here? Inside the square root, we have variance of error. Because what here, yi minus yi hat, your actual observation minus predicted value, that's error, right? So this is simply error squared, okay? Sum of squared error, SSE, divided by n minus 2, you can say that's error variance, okay? And if you take the square root, that's standard deviation of error, right? We call it standard error, okay? Okay, I think we're going to stop here today, and we'll continue. I already uploaded the next notes. Make sure you bring it on Tuesday, okay? All right, I'll see you next week. Have a good weekend.